Have you ever stopped to think about how our computers got so crazy fast? I mean, really fast. What if I told you the secret wasn't about adding more, complexity, but actually taking it away? It sounds a little backward, I know, but the story of our modern processors is this amazing lesson in the art of less is more.
It's a total paradox, right? Get simpler to go faster. But this one idea, this single thought, completely turned computer architecture on its head. And it's pretty much the reason the device you're watching this on right now is as powerful as it is. So let's dig in and see how it all works.
Okay, so to really get why this was such a brilliant solution, we first have to understand the problem. And back in the early days of computing, processors were heading straight for what you could call a complexity crisis.
So the big idea back then was something called CISC, which stands for Complex Instruction Set Computer. And the logic kind of made sense at the time. If you can make the hardware, the chip itself, understand really complex commands, well, that should make life way easier for the software programmers, right?
Think of it like this. A CISC processor is like a chef who has a single, massive recipe for bake and decorate a 3-tier layer cake. It's one incredibly powerful, but also incredibly complicated instruction that tries to do everything all at once. The whole goal was to bridge that gap between the code people were writing and the hardware that had to run.
And the result of all this complexity? Well, it was messy. Instructions weren't a standard size at all. One command might be super short, and the very next one could be enormous. Just imagine a factory conveyor belt where you've got these tiny little boxes followed by huge, awkward crates. It's inefficient, it's impossible to predict, and it makes optimizing the whole workflow an absolute nightmare.
But then, a few really smart engineers were looking at this complicated mess, and they asked a revolutionary question. What if we have this whole thing backwards? What if the real key to speed isn't adding complexity, but embracing radical simplicity?
And this huge shift in thinking was really driven by pioneers like John Hennessy at Stanford and David Patterson over at Berkeley. These guys looked at how things were being done. They challenged that whole way of thinking, and they ended up laying the foundation for the next 40 years of processor design.
Their answer was RISC, or Reduced Instruction Set Computer. So instead of that one giant complicated recipe, the RISC philosophy gives the chef a small set of simple, basic tools. Mix, bake, frost. Each one is simple, it's fast, and you can combine them to create that exact same complex cake, just in a much, much more efficient way.
So what does this RISC playbook actually look like when you put it into practice? What are the core rules of the game that make this whole less is more thing so incredibly powerful?
Well, it really boils down to 3 fundamental ideas. First, a small, simple set of instructions. Second, a fixed length for every single one of those instructions. And third, a really disciplined way of getting data from memory, which is known as a load/store architecture.
And this is where you can really see the difference in philosophy. CISC tries to do it all in one go, with one complex command, like go to memory, grab 2 numbers, add them together, and put the answer back. But RISC? Nah, it breaks that down. It says that's 3 separate jobs. You get 1 instruction to load, a second instruction to add, and a third instruction to store. Each step is clean and simple.
So if we go back to that conveyor belt analogy, the CISC approach is just a logistical nightmare for the processor. It has to waste precious time and energy just figuring out how big each instruction is before it can even think about what to do with it.
But the RISC solution? Oh, it's just beautifully simple. Every single instruction is the exact same size. For a modern architecture like RISC-V, that's a clean 32 bits. Every box on that conveyor belt is identical, and this makes the process of decoding and handling instructions incredibly fast and simple.
And that brings us to that crucial load/store model. A key rule in RISC is that the processor's core, the part doing the actual math, never works directly on data that's far away in the main computer memory. Think of that main memory as a giant, kind of slow warehouse. Instead, the processor has to first explicitly load the data it needs into these super-fast on-chip storage spots called registers. Think of registers like a small workbench right next to the worker. It does all the calculations there on the workbench, and only then does it explicitly store the result back in the big warehouse. It's a very deliberate process.
Okay, so simple instructions, fixed lengths, this whole load-store thing. Why does any of this matter? Well, it all comes together for one huge payoff, a concept that is the absolute cornerstone of modern performance, pipelining.
Pipelining is the ultimate performance hack. Instead of taking one instruction,
running it from start to finish, and then starting the next one, the processor works like a factory assembly line. It can be fetching one instruction, decoding a second one, and executing a third one, all at the exact same time. And this is where the genius of the RISC design just totally shines. Because every instruction is simple and uniform, they just flow through this pipeline perfectly. There are no weird variable length instructions jamming up the assembly line. It's a smooth, constant flow that allows the processor to complete, on average, close to one instruction for every single tick of its internal clock.
And how close does it get? Well, this number, 1.25, is the average cycles per instruction, or CPI, on a benchmark processor. Basically, it's how many clock ticks it takes to finish one instruction. Now, the dream, the perfect score, is 1.0. So getting to 1.25, that is a testament to the absolutely incredible efficiency that RISC simplicity unlocks. It is just phenomenally fast.
Okay. And this isn't just some abstract concept from a computer science textbook. RISC architecture is, quite literally, all around you. It's powering the technology you use every single day.
A perfect modern example of this is RISC-V. It's a cutting-edge RISC architecture. And get this, it's completely open and free for anyone to use. And it's already being used by major players. You can find it inside hard drives from Western Digital, it's used in NVIDIA GPUs for controlling things, and it's powering a whole new generation of hardware from companies like Sci-Fi. This is that less is more philosophy in action, right now.
So there you have it. For over 40 years, the big secret to going faster was actually to get simpler. This philosophy has powered everything from Moore's Law to the incredible computing power we all just take for granted now. It really makes you wonder, doesn't it? As we start to push the very limits of physics, what's the next paradox that will drive the next 40 years of computing? What comes after less is more?